Hello learners, welcome to the course Statistical Methods for Economics, Discrete Uniform Distribution. In this session, we will discuss the concepts related to discrete uniform distribution, properties and features of discrete uniform distribution, computation of discrete uniform probabilities, application of discrete uniform distribution in economics. In the previous module, we have discussed the concept of theoretical distributions, where the theoretical distributions are classified as discrete distribution and continuous distribution. The importance of theoretical distributions in economics were discussed in detail. In this session, we shall look into one of the discrete distribution, that is discrete uniform distribution. We shall first define what discrete uniform distribution is. The discrete uniform distribution is a probability distribution that describes the possible outcomes of a random experiment in which each outcome has an equal chance of occurring. In other words, if there are a finite number of possible outcomes, the probability of each outcome is the same. Formally, if we have a random variable x that can take on n distinct values, the discrete uniform distribution assigns a probability of 1 by n to each value of x. The probability mass function, that is PMF of x, is given by probability of x is equal to x is 1 divided by n for x is equal to 1, 2, 3 etc. up to n and 0 otherwise, where probability of x is equal to x is the probability that x takes on the value x. For example, consider a fair six-sided die. The possible outcomes are the numbers 1 through 6, and each outcome has an equal chance of occurring. Then, discrete uniform distribution models this situation, where each number has a probability of 1 by 6. The discrete uniform distribution is useful in a variety of contexts, such as in computer science, where it can be used to model the outcome of a random number generator. It is also used in sampling theory, where it can be used to ensure that each member of a population has an equal chance of being selected in a sample. Now, we shall look into certain properties of discrete uniform distribution. Probability mass function. The probability mass function PMF of a discrete uniform distribution is given by probability of x is equal to x is 1 divided by n for x is equal to 1, 2, 3 etc. up to n and 0 otherwise, where n is the number of possible outcomes and x is the random variable that represents the outcome. Using notations, we denote discrete uniform distribution as x follows uniform of n. The mean of a discrete uniform distribution is n plus 1 by 2. This means that the expected value of the distribution is the midpoint of the range of possible outcomes. the variance of the discrete uniform distribution is n square minus 1 by 12, which implies that standard deviation is equal to square root of n square minus 1 by 12. And it is to be noted that the variance increases as the number of possible outcomes increases. The median of the discrete uniform distribution is n plus 1 divided by 2. For a discrete uniform distribution, mode can be any value in the range of 1 to n. The skewness of a discrete uniform distribution is 0. The kurtosis of the discrete uniform distribution is minus 6 into n square plus 1 divided by 5 into n square minus 1. The cumulative distribution function of a discrete uniform distribution is given by f of x is equal to 0 if x is less than 0, x by n if x is equal to 1, 2, 3 etc. up to n, and 1 if x is equal to n. Constant probability. The probability of each possible outcome is constant and equal. This means that the probability of any particular outcome is always the same regardless of the other outcomes that have occurred. Finite support. The discrete uniform distribution has a finite support, which means that it only applies to a specific set of possible outcomes. For example, a die can only produce the numbers 1 through 6. So, the discrete uniform distribution apply only to those values. Independent events. If two events are independent and each has a discrete uniform distribution with the same number of possible outcomes, then the joint distribution of the two events is also a discrete uniform distribution. This property is useful in many applications such as probability theory and statistical analysis. Overall, the discrete uniform distribution is a simple and useful probability distribution that is used in many different fields, including statistics, computer science, and engineering. Its properties make it easy to work with and provide a useful framework for modeling random events with a finite number of possible outcomes. We shall now look into the computation of discrete uniform probabilities using a mass function. In an experiment of rolling a fair 6-sided dice using the discrete uniform distribution, compute the probability of rolling 3. Also, compute the probability of getting an even number. In the experiment of rolling a fair dice of 6 faces dice, that is n is equal to 6. Let us define the random variable x as the face shown up on the dice. The number of possible outcomes is 6. As the die is considered to be uniform, by considering the probability distribution of discrete uniform distribution, that is, probability of x is equal to x is 1 divided by n, for x is equal to 1, 2, 3, etc. up to n and 0 otherwise, where n is the possible outcomes. In this case, n is equal to 6. We have probability of x is equal to 3 is equal to 1 by 6. Similarly, to find the probability of rolling an even number, that is, the occurrence of 2, 4 or 6. As these events are mutually exclusive, we have probability of x is equal to 2 or probability of x is equal to 4 or probability of x is equal to 6 is equal to probability of x is equal to 2 plus probability of x is equal to 4 plus probability of x is equal to 6, which is equal to 1 by 6 plus 1 by 6 plus 1 by 6, which is equal to 3 by 6, which is equal to 1 by 2. A bag contains 10 marbles numbered from 1 to 10. Compute a probability of selecting any particular marble using a discrete uniform distribution. Compute the probability of selecting a marble numbered between 3 and 6, which is inclusive. Compute the probability of selecting a marble number greater than 10. In the experiment of selecting a marble from the bag, let us define the random variable x as the marbles in the bag. The number of possible outcomes is 10. That is, n is equal to 10. As the selection of the marble is considered to be uniform, we consider the probability distribution of discrete uniform distribution, that is, probability of x is equal to x is 1 divided by n for x is equal to 1, 2, 3, etc. up to n and 0 otherwise. Now, as all the marbles has an equal chance of being selected from the bag, the probability of selecting any marble is probability of x is equal to x is equal to 1 by 10. Sub-question A is answered as follows. Let us assume a marble numbered as 7 is to be selected in particular, then probability of x is equal to 7 is equal to 1 by 10. Sub-question B is answered as follows. To find the probability of selecting a marble numbered between 3 and 6, that is, the occurrence of 3, 4, 5 or 6. As these events are mutually exclusive, we have probability of x is equal to 3 or probability of x is equal to 4 or probability of x is equal to 5 or probability of x is equal to 6, that is equal to probability of x is equal to 3 plus probability of x is equal to 4 plus probability of x is equal to 5 plus probability of x is equal to 6, which is equal to 1 by 10 plus 1 by 10 plus 1 by 10 plus 1 by 10, which is equal to 4 by 10, which is equal to 2 by 5. Sub-question C is answered as follows. Since the maximum value of the range of possible outcomes is 10. There is no marble numbered greater than 10. So, the probability of selecting the marble number greater than 10 is 0. Let x be a random variable of discrete uniform distribution. The random variable x represents the number of dots on a fair die. The probability mass function is given by probability of x is equal to 1 by 6 for x is equal to 1, 2, 3, 4, 5, 6 and 0 otherwise. Then compute average of x, variance of x, standard deviation of x. From the given information, we have the PMF of the distribution is probability of x is equal to 1 by 6. For x is equal to 1, 2, 3, 4, 5, 6 and 0 otherwise. Now, this is a discrete uniform distribution and the mean of the distribution is expected value of x, which is equal to n plus 1 by 2, which is equal to 6 plus 1 divided by 2, which is equal to 3.5. The variance of a discrete uniform distribution is given by n square minus 1 divided by 12, which is equal to 6 square minus 1 divided by 12, which is equal to 35 divided by 12, which is equal to 2.9167. The standard deviation of the discrete uniform distribution is given by square root of variance, that is square root of 2.9167, which is equal to 1.7078. Hence, for the given distribution, the average is equal to 3.5, the variance is equal to 2.9167 and the standard deviation is equal to 1.7078. Now, we shall now look into the computation of discrete uniform probabilities using a distribution function. The cumulative distribution function of the discrete uniform distribution is defined as f of x is equal to 0 if x is less than 0, x by 6 for x is equal to 1, 2, 3, 4, 5, 6, 1 if x is greater than or equal to 6. Then what is the probability that the outcome is less than or equal to 3? What is the probability that the outcome is greater than 4? What is the probability that the outcome is exactly 2? What is the probability that the outcome is between 2 and 5, which is inclusive? Consider the given distribution function f of x is equal to 0 if x is less than 0, x by 6 for x is equal to 1, 2, 3, 4, 5, 6, 1 if x is greater than or equal to 6. Now, as we are given the distribution function, let us compute the required probabilities using the properties related with distribution function. Firstly, we are supposed to find the probability of the outcome less than or equal to 3, which is equal to probability of 1 less than or equal to x less than or equal to 3, which is equal to probability of x is equal to 1 plus f of 3 minus f of 1, which is equal to 1 by 6 plus 3 by 6 minus 1 by 6, which is equal to 3 by 6. Hence, the probability that the outcome is less than or equal to 3 is 3 by 6. Secondly, we are supposed to find the probability of the outcome greater than 4, which is equal to probability of 4 less than x less than or equal to 6, which is equal to f of 6 minus f of 4, which is equal to 1 minus 4 by 6, which is equal to 2 by 6. Hence, the probability that the outcome is greater than 4 is 2 by 6. With respect to the third sub-question, we are supposed to find the probability of x is equal to 2, which is equal to f of 2 minus f of 1, which is equal to 2 by 6 minus 1 by 6, which is equal to 1 by 6. Hence, the probability that the outcome is exactly equal to 2 is equal to 1 by 6. Now, as a part of fourth sub-question, we are supposed to find probability of 2 less than or equal to x less than or equal to 5, which is equal to probability of x is equal to 2 plus f of 5 minus f of 2, which is equal to 1 by 6 plus 5 by 6 minus 2 by 6, which is equal to 4 by 6. Hence, the probability that the outcome is between 2 and 5, which are inclusive, is 4 by 6. Consider a situation where a coin is flipped twice and the number of heads obtained is recorded. Let x be the number of heads obtained. Construct the distribution function. Compute the probability of x greater than 1. In the given situation, the experiment given is the coin is flipped twice and the number of heads are recorded as the random variable x. Hence, the possible value x can take is 0, 1, 2. Now, by definition, distribution function is given by f of x is equal to probability of x less than or equal to x, then f of 0 is equal to probability of x equal to 0, which is equal to 1 by 4. F of 1 is equal to probability of x less than or equal to 1, which is equal to probability of x is equal to 0 plus probability of x is equal to 1, which is equal to 1 by 4 plus 2 by 4, which is equal to 3 by 4. F of 2 is equal to probability of x less than or equal to 2, which is equal to probability of x is equal to 0 plus probability of x is equal to 1 plus probability of x is equal to 2, which is equal to 1 by 4 plus 2 by 4 plus 1 by 4, which is equal to 1. Now, we shall compute probability of x greater than or equal to 1, which is equal to 1 minus probability of x less than 1, which is equal to probability of x less than or equal to 0, which is equal to 1 minus 1 by 4, which is equal to 3 by 4. Hence, the probability of getting more than one head is 3 by 4. We shall now look into some applications of discrete uniform distribution. Modeling situations where all outcomes are equally likely. Modeling price changes where a product can be priced at several different levels. Generating random numbers to simulate uncertain events in economic models. Modeling the probability of a discrete event happening with equal likelihood. Modeling the number of potential outcomes in a given scenario, such as the number of bidders in an auction or the number of products a firm produces. Calculating probabilities for decision making under uncertainty, such as in game theory or risk analysis. Summarization. In this module, we have discussed about one of the theoretical distribution, that is discrete uniform distribution. We understood the probability mass function of the distribution, its cumulative distribution function, and the descriptive measures associated with it. In relevance to this distribution, some simple practical problems are solved using the probability mass function and the distribution function. Thank you.